Hello, everybody. So it is my pleasure to introduce today's speaker, Rai Weiss. Rai is an emeritus professor of physics at MIT and one of the founders of the LIGO gravitational wave observatories. So I think most of you know about 2.5 years ago, LIGO was successful at detecting for the first time gravitational waves as they passed through us here on Earth. As they passed through us, they changed the distances around us by only 1 part in 10 to the 21. It was a 100-year journey to go from the first prediction to this initial and only experimental result in gravitational waves. And Rai's vision, hard work, persistence over many, many decades was critical for this accomplishment. As you would imagine, Rai has achieved many awards and titles throughout his life. They seem almost impossible to enumerate. I should point out that not only for his work with LIGO, but also some of his original work on measuring the cosmic microwave background with the COBE mission. Of course, one of the most prestigious awards that he's received most recently is the Nobel Prize in Physics, granted in 2017. And I'm really excited to have his talk today because I believe he will give us his vision of the future of gravitational wave physics and astronomy, as well as what he thinks the challenges are. And given what we know about Rai, he will, I assume, inspire many of you to actually rise to actually solve some of these challenges in the coming decade. So please join me in thanking Rai Weiss.
Well, I just want to make sure that some of you are not in here under false pretenses. Really, I'm not going to talk about the discovery. Thank you for the introduction is all that will be about gravitational waves, pretty much. I'm going to talk mostly about technology, and that may not be interesting to many of you and the reason I've been doing that is because at one time there was a very first-class group here in technical parts that have to do with this business, and it'd be nice if there was a follow-on group here that does the same as part of the center. And so I'm going to mostly talk about technical things. And those of you who get bored very quickly, I will not be mad if you walk out. Really, it won't bother me at all. I mean, so look, you'll see the first slide already is a lesson. It's a pedagogic thing. Right? Look at that. Now, I'm going to be talking on that level for the most of the talk. I'll tell you what this is, and I don't want to make it totally hopeless for you, but what this is I want to explain these interferometers better than I can in a public lecture. I gave a public lecture, many of you probably weren't there, but it doesn't matter. But let me first start in the most primitive way. The reason why I want to be careful with this is because all the advances that you will hear from me that will change the properties of the detectors are really based, at least among the optics, on the ideas that are in this picture. You have to sort of get the idea of how it works. And the basic idea of the LIGO gravitational wave detector, I'll just say first, and then I'll go to the detail that this picture shows, is this is a Michelson interferometer. I don't know how many of you have ever played with a Michelson interferometer. I'm just curious. That's a substantial number of you. Okay, so this is not going to be totally hopeless. Okay. But the thing is that here's a laser. Here's a beam splitter. That's the thing that divides the light. And then there's some distant objects, mirrors. So these are masses, these distant things. And here's a gravitational wave that comes down. Now, I should have showed you a picture of what a gravitational wave does. And that much pedagogy I'll do. What the gravitational wave does is it stretches space in one dimension perpendicular to the direction it's moving. It's a transverse wave. A wave that's all its dirty work is perpendicular to the direction of motion. It's moving, we now know, at the velocity of light or damn close to it. Part in 10 to the 15 close to it. It's really quite spectacular. And the thing is that it comes and it stretches, let's say, one arm and shrinks the other. That's what it does. And so let me give you the basic idea, and then I'll go to the details, which are absolutely critical so you'll understand the future. The basic idea is very straightforward. We take the light and make this arm as long as that one. And if you do that, a beam splitter has this nice property, which is very important to us. This is a beam splitter. If you come in on one side of it, it makes no change in the electric field. It just reflects it, and it gets a little smaller. We'll see that in a minute. The other thing, another beam goes through this, hits that, comes back, but then it's reflected from the other side, where it's inverted. The electric field flips. That's very important. Otherwise, you can't conserve energy. And then many of you, well, if you do just E and M, and you'll see that this is what happens. And so there is an arrangement. If this arm is exactly equal to that arm, there will be no light going to the photodetector. And that's the most elemental way of talking about how this works. Because what the gravitational wave does, it destroys that equality. It makes, you made these exactly equal, no light goes here, this stretches a little bit, and that comes in a little bit, and that makes light appear at the photodetector. That's the most primitive way to think about it, but doesn't get you anywhere in terms of any progress. So I'm going to have to now introduce you to modulation. Okay, so let me do that. Let me do that by going to this slide, and I'll come back to that. This is probably, I don't want to insult anybody, but it's important even though that you know this. The kind of, here are different waveforms, and this is all just sinusoids. These are things you might learn in a course in electrical engineering, or you might learn in a moderately good course in electricity and magnetism. But let's see, here's what we call a carrier wave. That's just the electric field in a wave. This could be an optical wave, doesn't matter. And one way to think about it is as a phasor. This is now, think of this as in a diagram where this is the imaginary axis and that's the real axis. This thing rotates around at omega naught. And there's nothing on it, it just rotates at omega naught. That's the frequency that you see in this waveform. Okay? And there's a way to express that if you ever had a spectrum analyzer, a device that looks at all the amount of energy at each frequency, you would get only one line in this. And this says amplitude of the electric field, and that's the frequency of the electric field on the x-axis. So it has only one frequency. Okay? That's easy, right? So now you do something like what is on an AM radio. When you listen to an AM radio in a car, or not an FM radio, you put amplitude modulation on it. So what you'd have another frequency that modulates this. You see it? I mean, you can see that's the frequency. And that's this carrier. We call this the carrier frequency. And that now has something new in it. And if you now go to this diagram, what you've done to it is you've added a little thing. This is still rotating around at omega naught with this little new thing, which has some vectors in it that do the following. These are the modulation vectors that are associated with this amplitude modulation, and they change the length of the carrier. That's what they do. So you'll see that you take this is at a frequency, this is at a frequency modulation, the omega n, and there's a sideband. We'll see what that means in a minute, but you divide that up into two sidebands, one that is a frequency that's higher than the carrier, another one that's lower than the carrier by omega n. And this whole system turns around with that little ball at the end. It keeps going around and around. And here is the way you would represent that on your spectrum analyzer. You would represent the carriers, and then here is the lower sideband, the blue guy, and here is the upper sideband. And you would now see that there are actually three frequencies that are associated with this particular waveform. You with me? Yeah, I think that's all pretty straightforward. Okay, so now here's the other kind of modulation you can do. You'll notice there's no amplitude modulation. It's all phase modulation. You notice that the spacing at zero crossings isn't the same all across this. So there is now, and this is what you get on an FM radio, not an AM radio. Okay? And so now this is just a matter of how you organize the sidebands. It's still modulated at omega n, but now you notice the sidebands do this. When you collapse these two, remember this is turning, and this is turning with it, you either advance, you go backwards in pushing this backwards or forward. So you're adjusting the rate at which this thing's turning around, the phase of it. And that's the thing you have to pay attention to. And when we now talk about all the things that happen. So there's, okay, that's it. That's the lesson in electrical engineering that you need for this. Let's go back to the picture of the interferometer. So, okay, so I've made it so that I've tried to make the color coding the same, but I may not be perfect. What you see is little arrows. Here's the laser. Here, what's a purple arrow is the direction of propagation of a light. And this is the spectrum that would go with it. And so coming out of the laser is only the carrier. That's the big red thing. It comes and hits the mirror. And you'll go along with me. What I'm saying now is not totally right, but it's good for this little picture. It gets reduced in amplitude because the intensity is halved by this. So the electric field is 0.7 of what it was here. But it's going along and it hits this mirror. And let's say the mirror has now been driven at a frequency of omega n. And the light that comes off that mirror, because of the Doppler shift, you can think of it, of that modulation, you will get these two sidebands, these phase modulation sidebands. So the carrier comes off. If the mirror is a good reflector, that's the same height as that, or damn near close to it. And now here's a lower frequency sideband, and it has the opposite sign. These are phase modulation sidebands that come from the motion of that mirror, and they come back to the beam splitter. Okay, that's the first step. Now let's look at one that goes through is transmitted through the beam splitter, and that one here it is going toward the mirror, hitting the mirror. Mirror now. Remember now, I told you that the gravitational wave stretches one arm and contracts the other. There's always this push-pull motion that's associated with a gravitational wave. So again, you get sidebands, but they are the opposite phase. Here's the carrier coming back to the beam splitter, and this now is negative where that one was positive. Well, they come back, they hit this thing. Remember, there's a negative sign on reflection. It flips all the phases. And lo and behold, going back to the detector are only the sidebands that are big and doubled, but no carrier. That means there's no light at the photodetector, hardly any, except those sidebands. And what the gravitational wave has done, you can think of it as moving the mirrors. And I'll say in a minute, there's another way to think about this. What it has done is it made it so that all the sidebands power goes this way. You'll notice that coming back from the interferometer, these were opposite in phase. None of the sidebands go back to the laser. What comes back to the laser is all the carrier frequency. You got me? Good. That's lesson number 55 in gravity wave detection. And so now what happens is that there's another way to think about this. The light that goes to the photodetector has the difference in phase, or the difference in time of these two paths. The light that goes back to the laser has the sum of the times, or the sum of the times divided by 2 in it. And that's called so this side is called the symmetric side of the beam splitter, that side is called the anti-symmetric side of the beam splitter. And now, you don't detect sidebands. That's not so easy. They're very tiny. Remember, they get derived from the laser carrier by the motion. And if you have somehow, and we'll get to it in a minute, how this gets multiplied, but the important thing is you have to, if you're trying to do this experiment this way, you have to have a little bit of carrier left here so that can beat against, in the photodetector, so you can have a beat between the sidebands and the carrier so you can detect something. In other words, there is no net intensity in those two things. What you get is you have to have a little bit of carrier so you can hear this. And that's just a subtlety which is a subtlety, and let's not make too much of it. But I do want to say something which is not so obvious, and maybe Abe will argue with me. You don't need the mirrors to get the sidebands. Now, that's not that you have to get the light back to your detector, but it turns out there are other ways of thinking about this. For example, like the thing that's called LISA. If you solve Maxwell's equations in a gravitational field, do it right, you will get sidebands. Just do it. If you haven't done it, do it for yourself. It's a wonderful example. So it turns out the interaction of a gravitational wave with an electromagnetic wave makes sidebands. You don't need the mirrors to do it, but it's a nice way to explain what's going on. And of course, somehow you have to get the light back to the photodetector. If you let it go off like that, you're stuck. So anyway, that's the explanation of the interferometer. Are there any questions about that? Because it's important that we get this one right. Okay. All right. So, oh dear. Okay. All right, I'll have to do it that way. Sometimes this helps. Okay, so here's the real interferometer. This is the one that made the detector. And now I can walk you through that, and you'll understand it a little better. That's one of the Okay, so now you want the same picture. Whoops. Yeah. Here's the same picture. There's the laser. There's the beam splitter, the disk masses again. But now there's some more mirrors in here. That one, that one, that one. There are 4 more mirrors in this. Let's look at them individually. This mirror right there, which is at the input to this, makes it so that you bounce the light back and forth many times. It's a fancy word. It's called a Fabry-Perot cavity. And it's a way, if you make this slightly transparent, the beam will bounce back and forth and build up, but it'll leak out of this cavity with equivalent phase shift as though it had been bounced back and forth, let's say 300 times. Okay? And so the same thing happens over here. So effectively what you've done, one way to think about it, I like to think about it, is you bounce the carrier frequency back and forth, so the carrier is building up in there. It's 300 times bigger in amplitude, in intensity in the end. And what it has done is it made the sidebands larger just by doing that. That's one way. So you've increased the sidebands by the number of times you've bounced the light back and forth. That's a big step forward. And you still arrange to, wow, okay. This is going to run out of power. What that does is if you make this bounce, this identical in length and identical in reflectivity to that one, you will obtain the same condition, that no light goes through the photodetector when there's no gravitational wave there. But now you have about 300 times the sensitivity. About. So the next mirror you worry about is, actually I showed you before that all the light, if you do this, goes back to the laser. Now here's an invention that both Ron Drever and Roland Schilling, these are various high figures in this business, have had. Look, if all the light is coming back, it's not absorbed in the mirrors. Forget about that. That comes very much later. But it comes back to this. You could do a clever trick, and this is the trick. The trick is you take the laser light. This is a partially reflecting mirror again. And you take the laser light, and normally it would also have a beam coming back, because this is a mirror, really. So there would be one beam that comes up. I didn't draw it in here. It would come back again. And now you take that light that's coming out of the interferometer, which is almost all the light that left the laser, and it'll come through this because it's partially transmitting. And now you have a new interferometer you can make. The interferometer is the light that gets transmitted by this and the light that gets reflected by this. You make them cancel interferometrically. You just flip their phases. And so that says no light gets back to the laser. You get this picture, and this light in here gets built up. And it gets built up, for example, if you have 10 watts here at this place coming out, you might have something like 500 watts in here, and you might have 100,000 or maybe 200,000 watts in there. Okay? So you keep up building, you're keeping up to build up the carrier, and you get bigger and bigger sidebands. Now, what's this mirror do? That's a very clever mirror, but once you know about the sidebands, you know what it does, because there's no carrier here, right? So all that's here is sideband. And those sidebands get reflected. This is, again, a partially transmitting mirror. And those sidebands get reflected back into the interferometer. And when you do that, you can change the spectral response of the interferometer, how it responds to the gravitational wave. At what frequencies is it more sensitive than other frequencies? You can color the spectrum of the sensitivity of the device. And that was invented by Brian Mears, who was a graduate student at the time in Glasgow. So that's the full interferometer that actually made the detection. Okay? And it got, that interferometer breaks a fringe up. At the photodetector, you could break the fringe up into about 10 to the 11 parts. In other words, you have a gain over the wavelength in sensitivity. The wavelength is 10 to the minus 6 meters. You get down to 10 to the minus 18 meters. And that's what you need if you have a system which is 4 kilometers long, and you want to look at a strain that you said, whoop, there you are, 10 to the minus 21. So that was all the optics tricks are right there. Now I got to tell you about the mechanical tricks, because you still have to get rid of all the motion of those mirrors. But first, before I do that, let me show you the noise budget. Okay, this is, I did not show that in my lecture in the hall because it's a little too much for the audience. I thought, but for you guys, it shouldn't be. So what this is this is the noise budget for the first interferometer that we built, the first large interferometer. It's not, I'll show you the one for the one that made the detection, but this is a better picture, and it shows clearly some of the things you're up against. And yeah.
It's working. It's working.
Yeah, can you still see it?
Yeah.
I'll bring out my own. I mean,
yeah.
You have a better one. This is spectacular, this guy. Anyway, so this then is frequency on this axis, and this is like strain. It's a strain per bandwidth. So strain per root hertz. If you want to interpret, let's say, 10 to the minus 22 in this thing, sort of not quite. Here, you interpret the sort of the bottom of this picture, right about there. You take the bandwidth, take the square root of it, and multiply it by the y-axis. That gives you the RMS value, which is then a little better than 10 to the minus 21. So it's in 10 to the minus 22s. And so now here's the things that limited that first interferometer. I mean, you can see at high frequencies, and this still is true. We'll get how the improvements come. This is the ability to measure the position of the mirror due to the fact that you only have a finite number of photons to do it. And it's effectively the phase noise that we will talk about in a minute in the quantum noise. That's here. Then, let me go on. This is quantum noise. And then you can follow on the quantum noise over here. That wasn't the problem, and just barely now becoming the problem. And that's the radiation pressure noise. That's the other side of the quantum noise. And what you're drawing here, I'm drawing for you here, is the equivalent of the Heisenberg microscope, but done with a 70 kilogram or 40 kilogram object. In other words, remember the Heisenberg, how many of you have taken quantum mechanics? Okay, good. So the Heisenberg microscope is one where you send a photon at something small, like an electron. And then you say, I'd like to find out where it is. But you find out two things. The shorter the wavelength of your radiation, the better you do. And the more photons you can send at, the better off you are in finding it. But if you do all of that, the shorter wavelength and the more photons kicks the damn thing around. And that's the kicking around is this side. And so this is not something that's troubling us, but this combined curve is the quantum noise. And you'll see that plays a big role in a few minutes. But it was only, and then there is thermal noise, which this happens to be the thermal noise of the pendulum. Now all those mirrors are supported by pendulum. You'll see in a minute very elegant pendula that do better than the initial interferometer did. But that is just the fact that you're dealing with a system that's at 300 degrees Kelvin, and it has to satisfy the fluctuation dissipation theorem, which many of you don't know, but what that does say is if you have a system that is mechanically lossy, it also will fluctuate thermally. It'll fluctuate thermally. So those two things are related. Dissipation with fluctuations are related. And this happens to be a pendulum which is a little bit noisy. It's not due to the molecules that are hitting it. It's the actual structure itself has phonons running around in it, and that you have to worry about. And that made this little bit of noise. And this noise is very understandable and very painful. That's the noise of the ground, isolated by various springs and masses already. So that made the envelope of the initial detector. Now let's look at two other noises in this, and then I'll leave this. The other noise, which is the one that was so expensive and will turn out to be very critical when we think about third generation detectors, is the noise of the residual gas. I mean, here's, for example, if you have, in the 4-kilometer system, you have 10 to the minus 6 torr, you will get a flat noise spectrum that rolls over. And what's that due to? It's the fact that the number of atoms that are in the column, in the laser beam itself, inside the big long tubes, encounters, the number of atoms isn't always the same because they're going through the beam. And the fluctuation in the number of atoms in the beam determines how much forward scattering you have. And forward scattering of the light is the same as when you calculate the index of refraction. So it's a fluctuating index of refraction. And you need to pump the gas out to do that. And that, of course, is where the money goes. So here's, for example, 10 to the minus 9 torr. You gain only with the square root of the pressure. It's a slow gain. And LIGO right now is at this point. So that was where the money went. And here's a problem which causes you to demand that you have LISA, which is that satellite experiment. And this is a very important now noise for the future. This is a noise that has to do with not so much accelerations of the ground, which is what the seismic does. We'll get to that. But this has to do with something different. This has to do with the fact that if you have these mirrors, like these very good mirrors, and you've got them on the very good suspension, and they're not moving because the ground is accelerating, they still get forces on them. And the forces are that here's the atmosphere with lumps of density change, and it's flying over you. Or the ground motion that makes the accelerations has density changes in the ground. They then, those higher density places pull on the mirror harder than the low density places. They actually, you're doing a Cavendish experiment with the noise in the ground and with the atmosphere. And that's that curve. And it's a devastating curve because look how quickly it rises with frequency, with 1 over the frequency. So it turns out I have no expectations for a ground detector that'll do something at a hertz or even below a hertz. And most of us, as you'll see the other curves, you're probably not going to get much below 10 hertz on the ground. That's even true for the things we'll be telling you later.
What is the vacuum for LISA? What is the pressure?
No, you can have a slightly relaxed pressure, but then you lose. So I'll tell you about that when we get there. You might as well count down 10 to the minus 9.
No, but for LISA, what is it?
For LISA, no, the pressure out there is zilch. It's way below that, another factor of 1,000.
1,000?
Oh yeah, at least 1,000. I don't even worry about it. I mean, look, they're in Earth orbit. Excuse me, they're in the orbit of the Earth at the distance of the sun. They're right behind us.
Yeah, I don't know what the, okay.
Yeah, and out there, I mean, it's a particle per cc. I mean, this is still 10 to the 9 times 16. This is still 10 to the 7 particles per cc. Okay, it's huge. Okay, so, all right. Since I can see already I'm not running out of time, I thought this would be over with already by now. It is too much talking, but nevertheless, this is the progress of the initial detector. I just want to show you that because that's the hard work of a lot of people. But you look at the orders. This is now in position, not in. This is just if you want to get the strain, divide by 4,000. This is just the position noise, and it's a function of epoch. These are different curves. You can see what they are. Eventually, we quit, and this is a political statement. You can see that at the very end. Well, wait, this is still an initial LIGO. You'll see here's a curve that is the design curve. You can see we didn't make the design at frequencies, at very low frequencies, but we started making the design at about 50 hertz. And from then on, the design is buried in the actuality. And because of that, we did pretty well. I don't mean to be prideful, but we did enough well, especially where people were so skeptical of this to start with, that they gave us the money to build advanced LIGO. This demonstration, although it detected absolutely nothing, and I kept saying to people, we detected a good nothing. I said that in my other lecture. A good nothing means something. It means that you can count on that there wasn't anything at that level, and we were not quibbling with you that you should interpret our data and say, maybe you'll find a gravitational wave in it. We saw nothing. And that was that's a powerful statement. If we had said what sometimes the bar people said, look in our data, maybe you'll find something. That's not fair. Okay? So there was nothing there, that we, at least from our data analysis, and people are still looking at it, but they're not finding much. So here's what were the changes that were made for advanced LIGO. Now I've already told you what the detector optics looks like. Here's the mechanics part of it. And there's the same curve, we'll talk a little about that in a minute. And so there were two monster changes that were made, all at low frequencies. And here is the isolation system, which is a pendulum. These springs are attached to the ground. They give a little vertical isolation. They're cantilever springs. And here's one big mass. It's the first pendulum. And that mass this one hangs from that one. That's the second pendulum. That one hangs from this one. That's almost the same size as the mirror. And here's this precious mirror. And behind it is a whole other chain of things. You'll see that there's two masses down there. And this mass, which is the one with the mirror, is actuated by an electric field between this mass and that mass, electric field gradients. You have to suspend the thing that other end of the capacitor, otherwise noise gets, if this was attached to the ground, you couldn't operate because it would be wiggling too much and the electric field would transmit the vibrations of this mass to that one. So that's why you have to have that. And this, by the way, was designed by the Scott School, the Glasgow group. And then this is only the beginning. So you get an isolation that goes, as each one of these stages gives you an isolation at higher frequencies, above the pendulum frequencies, of about 1 over omega squared. So you get an isolation of what's going on of 1 over omega to the squared times 4 to the 4th power, so to omega to the 8th. That's just barely enough. It doesn't work very close to the pendulum frequency. So another thing was added. And you'll see here is this, and this is quite elaborate, but this thing is hanging from another thing inside, and this is an active vibration isolation system. And I will only point out what is in it, and I'll tell you what it does. This is a device that measures here's the platform, you can see this hanging from. And that platform hangs from this platform, so it's delicate, you hear some springs. But the important idea is that you have a seismometer, a very good seismometer, sitting there that measures the motion on the platform. It does it because a seismometer responds to motions relative to the fixed stars. Not relative to the can, not relative to, it's the fixed stars. So you have an inertial reference, and that's why I don't worry about seismic noise. And you'll see seismic noise, you can always do better on seismic noise. As long as you have good instruments that measure the relative motion to the stars. And so what is done, this is done twice, and what's happened here is that you take that seismometer and you push on it with actuators. Here's, for example, actuators that push on it. And what you do, you null the seismometer. You put the seismometer signal into the controllers, push on it with the opposite phase, and kill the motion of the seismometer, which means it's killing the motion of the platform.
So Ray, isn't there a delay between the actuator and that?
Yeah, maybe 10 to the minus 6 seconds. I mean, come on, sure. And yeah, that limits the loop gain you can have. But you can always do better. Right now, for example, we have started a revolution in seismometer design. Because what happens, I don't know how they work, they're usually magnetic pickups, inductive pickups, with magnets and coils. And then they started doing electrostatics, which is okay, but now the actuators are, not the actuators, the sensors are optical interferometers, and it has made a vast improvement in the seismometer. You can't buy these yet, the industry's doing it. I'll tell you, there's no limit. I mean, the limit will be the thermal noise in the seismometer in the end, okay? So, and they're nowhere near that in most cases yet, but they're getting closer, okay? So, look, I don't see that, the reason why I'm making a fuss about this, yes, we probably need a little better isolation than what you would just have here. But if you go to that 40-kilometer system, you'll hear about at the end, this is perfectly adequate for it. in many cases, you don't have to, there are other places you have to work hard, okay? But not there, it turns out.
Yeah, it was in the context of 40 kilometer I was asking.
Yeah, yeah.
But this is still for frequencies above 10 hertz.
What?
For frequencies above 10 hertz.
Yeah, but that has to do not with the seismometer. That has to do with the gravity gradients, and they
Exactly.
have nothing to do with that thing.
Right, but we're still limited that.
You can do a little there. Look, I'll make the argument right there. It's a little out of context, but that's the reason why making the length longer is so critical. All the noises. Maybe I'll get to it there. Maybe I should do it there. It turns out almost all the noises we know about don't matter because you're increasing the gravitational wave displacement at the ends. That's why you win with the long arm. And there are not very many noise sources that grow with the length. And I'll talk about that when I get there, okay? So it's, I think, a better scheme than making it underground at 10, well, we'll get to that.
Excuse me?
Okay.
How do you avoid killing the signal with the active damping?
How do you do, what, no, the signal, the signal is local. See, remember it's a strain. The gravitational wave is a strain. So if you do something at one end, you don't kill the gravitational wave signal. It moves everything together. If you took the two ends and started servoing them, which we do,
Right.
then you begin to kill the gravitational wave signal. But that's a different story. We'll get to that. Okay, are you with me?
Yeah.
Okay.
What are you doing? Low frequency? What are the seismic frequencies?
Okay, so very good. What this does is above the pendulum frequency it isolates. Pendulum frequency is around 1 hertz.
Okay.
It really only becomes effective at about 10 hertz. This goes from about 20 hertz toward about 0.1 hertz. And then it craps out for various reasons. And something we could fix. We have to fix at some point if you want to even get lower. I'll tell you where that becomes important. That becomes important in duty cycle. In other words, the biggest seismic noise we have is called the microseism. And the microseism are the waves hitting the shore. And you see two peaks, sort of. If you go to the shoreline, you see exactly what's causing the trouble. You see the waves coming in at sort of once every 10 seconds, and there's another group that come in every 3 seconds. Depends where you are. And you can see the Atlantic Ocean, you can see every storm in the ocean. And in California, in Washington State, you can see every storm on the Pacific. So if we want to, and what happens is that causes the servo systems that are holding the interferometer at a fixed point. This is the way, by the way, I should mention that. This is a trick that Bob Dickey taught us all. When you want to do a mechanical experiment, this is not shown in my slides, but when you want to, if you're interested in doing precision mechanical experiment, what you want to do is you never want to let the thing run free. In other words, you never want to leave the thing completely free. What you want to do is you want to make sure that you have a servo system around it that holds it fixed. And you record the amount of force that's needed to hold it fixed. Because what does that do? That allows you to damp the system in a way that's under your control. It doesn't, and you can also damp all sorts of normal modes it has that are uninteresting to you, but can screw up the measurement by nonlinear couplings. So it's an enormously important trick for doing mechanical experiments. And that LIGO has probably 10,000 servo loops in it, just for that. For different pieces in the electronics and the mechanics. We try to keep everything stationary and use the signals that use the signals that are used to hold them stationary as the output signal. Okay.
How is it mechanically done like this?
How's it mechanically done? Okay. Well, look, it's done here. Well, okay. Go back to that interferometer. And what you do is you lock it on a fringe, meaning you won't let the fringe move. And the way you do that, in this case, is in this case, well, okay, this is complicated, but what you have is, here's this, what we call a recoil mass, and here is the actual mirror, okay? And behind this, well, let me draw it, well, maybe, I'll explain it. So the recoil mass has a whole bunch of electrodes painted on it. And though there's an electrostatic force, that applies, well, the way it works is that electrostatic force is these are gradients of the electric field. That's how you make it. And you induce a dipole in this quartz. That dipole is induced by the electric field. So you have one power of the electric field in it. And then the force on the dipole is the gradient in the electric field. So it's the dEdx of the field times the field that pushes this mass. But it only does, it actually only pulls it. That's what you get. But then you bias it off so that you understand, but it's a force that's always pulling. But you make it more pulling or less pulling, depending on, and that holds the thing at a fixed fringe. So the output interferometer, at the interferometer, you don't let the fringes move. In fact, you lock the system up, and that's how we get our data. And with the data then, is the force that's holding that. Now, I've overdone it in a little bit because, I mean, Shad knows well because he has to correct for a transfer function. This is not a simple, when you get the output signal of LIGO, it isn't simply just you have to remove a 1 over omega to the 8th. No, there's much more you have to remove. And so you have to know that at some frequencies, at some are higher frequencies, like, for example, several hundred hertz, the feedback loops aren't holding the mass anymore. Okay? And so you actually have to look at the fringes and not subtract out the servo signal. So that's a delicate piece of it, and that's part of the calibration of the instrument. So it's not, well, I guess what I'm trying to say is that it's a mixture. In some places, the masses are totally free. At high frequencies, the servos don't really do much. At lower frequencies, they do a lot. And at DC, it's all servo. So you have to know what that function looks like. That's the calibration function of the instrument. I don't know how well you do this. I mean, you trust us for doing the calibration, or do you do it yourself?
We trust you.
What?
Yeah.
We trust you.
All right. Anyway, look, I'm gonna get into trouble. All right. Okay. So anyway,
There's a question.
one more.
I was wondering about how this applies to Lisa, because it can't.
It does not apply to Lisa. Lisa has it. I'll show you that. Lisa has its own little thing with thrusters. You'll see. Okay, if I get that far, I may not get that far. But this is now the noise curve, and you can see what dominates. Now this is the one that's now you're getting into our problems, and our current problems. And this picture is again frequency versus strain, and here's the curve that's the sum of all the noises. That black one, and you can see a big thing that really dominates the scene, which is this. Especially in the interesting region, where the system works well, near the minimum, the thing that's going to kill us, unless we fix it, is this red line. And what is that red line? You can see it. So it says so. Now, where's the red line? It's like the coding Brownian noise. Let me tell you what that is. And that's a research area that's actually critical to us. And that is that, although we now know how to tame the thermal noise of the pendula, and that was done by using quartz filaments here, and not metal ones, because the losses in quartz are a lot less. Bending losses in quartz are a lot less than in the metal fibers we used initially. And so we no longer have the thermal noise. You can see the thermal noise of the pendulum. I think that's in this drawing too. Does it show thermal noise?
The fourth one.
No, not coding. Where is it?
Fourth one.
That one, yeah. Suspension thermal noise. It's this thing now. That hardly matters anymore. We can do better, but it's not really determining this curve so much. It's this guy that's really, and what this thing is a thing which we hadn't thought of, to be honest with you, in the beginning. Ed Purcell had thought of it. I mean, he's my hero for many reasons, but, and what it is that when you deposit a coating, optical coating, and we have all these requirements on the optic coatings. They can't be scattering, they can't be lossy for the optics, they shouldn't be mechanically bad, but they are. And when they're mechanically bad because of the following. They're lossy mechanically. That's what I'm saying. The phonons in the coatings get scattered easily and they get absorbed effectively. So it turns out the dominant source of thermal excitation, that thing which says, where is the dissipation? In this mechanical dissipation, it's in the coatings, and that causes noise. It says the surface is not well defined at the level of, well, down to 10 to the minus 18 meters. That's where it's not well defined. And it's not because it's a granularity of the surface. That you can just, by making the beam bigger, you can take care of that. It's because the surface is wiggling at that level, at high frequencies, low frequencies, all frequencies. And it's due to the fact that a coating is an amorphous, crappy surface. It's not a single crystal. You lay down a coating and with evaporation techniques, and you get little mountains. And these mountains tend to slowly over time, and you have 50 layers of coating. And they begin slowly but surely to diffuse around and hop around. And that's the problem, and that's one of our big, how do you make a mechanically not lossy, loss-free coating surface? And that's a huge effort is being attempted. People are interested to think about that. I've had a session with some people last night about that here. That's a big issue. It has to be solved, as you'll see when you go on now. So there are other noises in this thing which are now, well, some of the, for example, you can see that what's called the quantum noise, which is this thing, this reddish thing. Well, this is okay. You can see that's getting to the point now where, it always dominated at high frequencies. But now it's beginning to be close to be, in fact, it's pretty much the whole story in this region right in there. And then this this noise, we talked about thermal noise, and but then here's that gradient noise, or the Newtonian gradient noise. It's beginning to get there. It's not yet the biggest problem, okay? So that's the situation with advanced LIGO. Now let me try to show you the real world. Here's the real world. And this is now, I think I'll be, I've got 20 minutes, is that okay?
Yeah.
Okay. So here, this is now the same kind of curve with real data. This is now, again, spectral density of strain, and this is frequency. And here is there's a detector in Italy. And this is, they were running with us, and finally, in August of last year, they also detected a black hole, which was absolutely critical for us. And that allowed better positioning in the sky. I don't want to go into that. I'm not talking about science right now. I'm talking about a different science. And so this is their noise curve, which is the worst in this picture, but it'll get better. Here's the noise curve of advanced LIGO back when the discoveries were being made last. And let's lower. There it is. And you can see what it's doing. And here is the design for LIGO, advanced LIGO. Look, this is this green line, which is very important to recognize. We are not a design, okay? And so that's what we're working on. And we're not designed in a couple of places. And you'll see what they are. This has to do with parametric instability. We'll talk about what that is. Down at lower frequencies, in this region right in here, between 100 hertz, the bucket, as people call it, the place that's a wonderfully sensitive place where the first detections are all made, we're in trouble because we don't know what's causing the noise. And I'll give you some of the things we're trying to fix, because we're not sure, and we're fixing a lot of things we know could be the problem. And this is a thing that I think all of you ought to know, is we're not going to be running again, really, until the apparatus is being fixed and worked on right now. Sometime, I don't know when that's over, it depends on how well things go. We hope sometime in the end of the summer, maybe, we will finally have everything done, and we begin to commission this instrument. And what we learned during the commissioning is whether we succeeded in getting rid of that noise. And I, for one, will vote against running again until we have fixed and found out what that is. That'll make you mad, I know. Go.
Why is the Virgo design curve?
Okay, I can tell you that. That's thank you. Okay, so the Virgo, I haven't got there yet, but that's a good question. You saw it. The Virgo design is this complicated-looking thing here, and it's made deliberately to match LIGO as well as it can because they want to get coincidences with LIGO. Well, they're on the way to getting that. This is the one where they made the detection. This is the curve that they made the detection. So they'd like to be at the same place as we are, but and they're not going to be very good, for example, at looking at the high frequency noise that Sasha is up. Where's Sasha? There you go. That Sasha and Rosola, and the whole paper, which was, I think, I have a picture of it if you want to show it, but there are possible very new interesting things that are possible with neutron star collisions. High frequency oscillations would be absolutely fantastic to see. And it turns out, I think they caught themselves out of it because of this, okay? Because LIGO, it turns out, according to Sasha, LIGO, this curve that is right here is in that paper he wrote. And it does have a couple of those things peering up out of the noise, okay? And I'm looking forward to that. I hope you're right. So it turns out, but I don't think it'll be Virgo. It won't be a coincidence measurement. That's the trouble. And so anyway, now, why is it this different curve? I'll tell you why. There are two reasons. One of them is 3 kilometers versus 4 kilometers, but that's one of the reasons. That helps all. That's a factor of 3/4. It can never be 3. That 3/4 will always be there. The other thing has to do with their own internal structure, how they designed the interferometer. They can't add more optics to the interferometer in an easy way because they made a decision very early on to build great big towers as for vibration. Their vibration isolation system is effectively multiple pendulum, many more than what we are using in the tanks in our thing. Many more, but they're very elegant and they're very tall and they're very expensive and there isn't much room. And they can't add more towers. And they refuse to put more optics on one tower. They may ultimately change their mind about that, but there was a huge debate within the Virgo project of trying to do this. They need to reconfigure the optics to bring this down. And the reason why is they're dealing with the same optical configuration that LIGO 1 has had. And I won't go into this, it has a flaw. It has an instability. And you have to add more optics to get rid of that instability. And LIGO was able to do that because we don't mind putting more mirrors into our much cruder vibration isolation system. No more, you can ask me more later. But there's a reason which worries me a lot that Virgo will continually have to fight somehow. They're trying to do things at high frequencies by using more laser power, and we'll get to that in a minute. If they want to bring this down, they have to use more laser power. Okay? But they have to do things which we're scared of. Okay? So, now, let me go on. This is what you're going to hear more about. So, we're not yet at design. We don't know why. If we get to design, and I don't know how much our feet will be held to the fire, there is a next thing which already we're proposing and we're studying, which is LIGO, which is called A+. Now, that's a theoretical curve, of course. It's a design curve. But it's another factor of around 1.7 better. And since the rate of events is such a strong power of the sensitivity, it's worth taking small factors. A factor of 2 is a factor of 8 in rate. That's because of the volume of the universe you're looking at. So it's very different than building bigger telescopes. This is a strong function of this. Everything we do is a strong function of the sensitivity. The ability to look for small changes, look for the fact that there's a violation of general relativity, all of that, all the science depends on sensitivity. It's a very different situation than other things in optics. And unfortunately, many of the people in the scientific community don't know that. They don't understand it. And they think, why don't you just keep running? Keep running. What's wrong with you? And I keep getting pelted by that over and over again. And I say, why? Because if we can figure out how to get a factor of 2 out of this thing, my God, wouldn't you be happy with 10 times the number of sources? Oh, of course. But they don't say that. Okay, so you've got to get that argument across. So if you have buddies who say, why the hell are they spending money? Explain this to them, okay? And so anyway, here is then, okay, I'm going to use my own. You need batteries for that. Don't go running for batteries. I have my own somewhere.
You can also use the stick if you want, right?
Yeah, there's a stick. Oh, really? That's wonderful. Let me see if this guy does the job. Okay, but this is modern. I got to do modern. Hold on. Give me the stick in a second. There we go. All right, good. It still works. Anyway, so then there is this idea. We'll talk about each of these if we get to time. What are the necessary things? Here is a thing which is sort of the very last idea we've had that you can still do within the. It's another factor of a little over 2. Within Voyager. That's a new idea, concept. It's still within the 4-kilometer systems that have been paid for. The same infrastructure is going to be used. It has some dramatic changes, we'll get to that. And then here are, below this, are 2 ideas. This is something called the Einstein. It's one version of the Einstein telescope. The Europeans are thinking very hard about this. I'm not going to say much more about that than just in this picture, because it's a design study that they've done. They have not costed it. They have no idea. They have a very good science case. You worked on that science case, but at this moment they have what I think still a hodgepodge of how they might do. I'm not saying that we don't have a hodgepodge too, but I want to show you what happens if you make a 40-kilometer system. This system, by the way, is a 10-kilometer triangle. Has some elegant ideas, buried underground, which reduces some of the noises. We'll get to that. This system, which doesn't necessarily have to be better than Einstein, just a curve or a design curve, it's called Cosmic Explorer. It's an idea that has been rampant within the LIGO community, and it's an idea of doing just what we did on the surface of the Earth, doing it with a system that's 40 kilometers long. And now let me show you what the problems are for this. Oh God, I'm not going to have time to do all this.
No, it's okay. We can go.
What?
We can go a few minutes over.
Well, all right. What I'm worried about, not me. I'm worried about you guys. Look, I'm not going to explain all of this, except this is I was going to do a little pedagogy on the improvements. But I just tell you, I'm not going to do this because I just want to point out something to you. I'll do it fast, and you may not get it. But this is that was a very important discovery made by Carlton Cades, which is important for you to know about. Maybe the diagram I don't have to explain the whole diagram to you. What Carlton Cades discovered is that quantum noise, which is the radiation pressure fluctuations, as well as the phase fluctuations at high frequencies, are all due to that 1/2 h bar omega that is in the background field, the radiation field, that quantum fluctuation, that is the 0-point fluctuations in the radiation field. That is in the mode that's determined by the laser beam in the system. And so you can count the modes. They're easy. The TE00 mode, it's one mode of the radiation field. You do the quantum calculation for what is the lowest number of photons that are in that state, and you find that 1/2 h bar omega will be in that state. So now where does that 1/2 h bar omega come into the interferometer? And that was the clever thing. What he found is that you bring it in from the front. Here's the laser. There's the beam splitter. That's just a standard Michelson interferometer. It comes in from the antisymmetric port. That's where it comes in. And it turns out, if you look at, I can't do it all because I won't have the time, it turns out that there's cancellations for all the noise coming in from the symmetric port. And so so what that has, if you follow through the logic, and I'll give you this slide, I mean, I'll give you this slide to you. What happens is that you find out that not only does, because of the negative sign of the beam splitter on this side, the positive sign, and follow a fluctuation field like that one into the system and see what it does, goes back and forth, and it turns out it comes back out again. One that comes in here gets flipped in sign, so it doesn't get there. On the other hand, the radiation pressure forces only are important because of this minus sign of the flipping here. They do the same thing. These are the different coherent, incoherent fields that come in from one point and the other, and you'll see that the radiation pressure terms actually show up as a push on the thing, but they don't show up here. They only show up here because they're a phase difference, and they show up again back at the antisymmetric port. So that key idea. We all had it wrong, by the way. Chip had it wrong. I had it wrong. Ron Drever had it wrong. We didn't. All got the right answer for the wrong reasons. Okay. So it turns out that this committee came up with something that was absolutely crucial to the design of this. And the way to say it again is the fluctuations in the background radiation field come in the antisymmetric port, the port where the detector is. When you set up the interferometer to have a null for the carrier at the antisymmetric port. So here's some things that have been done. The Germans squeezed. I'll get back to what a squeezing is in a second. And here is, for example, a Geo 600. They've been running their interferometer, which is a Michelson interferometer. And here's when they use, this is without squeezing, and I'll explain squeezing in a second. Here's what happens when they use a specifically tailored way of occupying that antisymmetric port. We'll show you that in a minute. You get an improvement at the high frequencies. It's not easy to get. You get improvements like that also if you have more power. Here's the thing that was tried at LIGO. Right after the initial detector, we tried it, and we got a little bit of improvement. But the reason we did it, it's not as good as that, but we were much more sensitive. And to us, the worry we had is when we squeeze the light and do all that mechanics, does it screw up the low frequencies where we're so worried? And it doesn't. That's what was, you see this, the Germans couldn't have done that because they've never quite figured out what the noise is at low frequency. So the Germans have been running squeezing light for several years now. LIGO is going to do that in this run, the next coming run. And so here is what a squeezer does. And this applies to all the advanced detectors that I talked about. It's going to be started in LIGO now. We're going to put a squeezer that's called not frequency-dependent squeezing, just exactly what you saw in the other picture, to try to improve, it's effectively the same thing as increasing the power. And we'll get to, we will do both, increase the power and use squeezing. And let me now explain squeezing to you also, you at least have a vague idea what it is. Squeezing is a way of doing the following. Once you recognize that you are dealing with a virtual photon that's coming in from the antisymmetric port, you put a nonlinear device, and that's what's happening here. You see, here's the interferometer, simple Michelson. Well, Michelson probably Pro, and here's the antisymmetric port. And what you do is you, in this device, which I will only describe to you in words and not exactly what goes on, this is the squeezer. And what it does is, and you feed that light into the interferometer in the antisymmetric port. And what are you doing? What you're doing is something really smart. I mean, it's clever as hell, and people love to do this, and it's something that people have, they love quantum optics. I know they do, and it's hard, but it's fun. And what it is that you take that virtual photon that's in the same mode as the one that caused you all that trouble, and you put it into a nonlinear optic. This is the nonlinear optic, but you make a second harmonic generator, thing that doubles the light, doubles the frequency of light, goes into that nonlinear optic, and that makes, as one of the products it makes two photons at half the frequency. So at the frequency of the light that you're using in the interferometer. So you have two 1 micron photons, and they're generated by effectively induced emission by that fluctuating photon that is the background fluctuation of the radiation field. So what you get thereby is you get two photons, they're entangled, and they're entangled by the way you want them to be entangled. You can make it so, and this is what's going on in this picture, you can entangle them in such a way that you can make it so that they're sidebands, the two together. You calculate those sidebands that I showed you in that picture, and you can do the following. You can make it so that in this region of the spectrum at high frequencies, over here, you can make it so that the sidebands that they are Now you've taken that photon, that's recreated it as a second photon in that nonlinear device, and so their sidebands are only amplitude sidebands. Okay? And now those, if you have the interferometer balanced, you don't have any carrier here, so it doesn't care if the carrier is going up and down a little bit. But so you make the two photons entangled so the sidebands are amplitude. But down here, on the other side, at low frequencies, and this is not, this by the way, what I'm describing now is not going to be done in advanced LIGO, it'll be done in A+. They will do frequency dependent squeezing. What's going to be done in initial LIGO is only one-sided, the high frequency, the thing you saw in the other picture. But this is being prepared and thought about, and now if you do that, and you organize the nonlinear medium in such a way that instead of getting the two amplitude sidebands, you get phase modulated sidebands, that won't push the mass around. Because you're just moving the vector around, you're not changing the amplitude. And the amplitude is what causes the radiation pressure to change. So it's a very elegant idea. And this is it's now been proved that you can do this. You need a cavity to do that flipping of AM to FM. And then you come into the interferometer with having effectively taken that 1/2 h bar omega and converted it into two photons, which are organized the way you'd like to have them. So that's the idea of squeezing. And now here's sort of what you get. This is now A+, a picture for A+. Again, a design drawing. Here is the total. I've asked. This picture has two pieces for the quantum noise. One, if you don't squeeze, it's up in here, the black line up there. Sorry, not the black line, the purple line. The purple line. And if you don't squeeze, and if you squeeze and do this dual frequency squeezing about 6 dB of it, no, 4 dB of it, excuse me, 4 dB of it, then you get this purple line like that. It's a significant change. Okay? So that's what's going to be done on A+ to make it better, among other things. And now, and there is mandated in this that we have somehow solved some fraction of the noise from the coatings. And so that's how we got that A+ curve. Let me show you what that is again. The A+ curve is this. This is the LIGO design. This is A+, and that involves that you have fixed somewhat of the coating noise. You've done very little else. And I'll make you now lists of various things.
Is there a time? Is there a in terms of planning when A+ might actually come online or something? Is there some timeline?
Oh yeah. Well, we're trying to get money for it right now. In fact, it's being reviewed. A+ is probably 2023, something like that. Look, that's probably optimistic. It's in the mid-20s. Okay, it depends a lot on how. Look, Abe. It depends. A lot of it depends on if we find out what really is wrong with the design of advanced LIGO. If we don't do that, we're stuck. We're going to have to keep working on it. You know,
do you think you'll make LIGO India A+?
We'll have to do whatever is going on in the United States has to be what's going on in India. Absolutely. We're crazy not to.
Exactly.
Oh, no. That's part of the agreement. Now, who pays for it? I don't know. I don't know. I don't think that's been ever argued about.
No, that's right.
And so anyway, so let's go on. Okay, so here's the other new thing that's happened. This is now LIGO. Why are we a little more confident that we can get all the power? This is a cute idea that was had by Matt Evans. And let me tell you a problem. Oh boy. Yeah. I can give you a problem that I won't say more than the following. It's described in this picture what the problem is. And it's Vladimir Brzezinski predicted this about 15 years ago. And what he predicted is once you have a big cavity, and you have a mirror, you have a problem which is the following. You can have, the mirror will have different normal modes of motion. Not just back and forth, but you do internal modes of the mirror. And here are some internal modes of the mirror. They could look like that, some mechanical modes. And here's the field inside the cavity, if it is scattered by the surface, will not necessarily fit into the mode that is the TE00 mode. There are other modes of the radiation field which have slight angles in them. They're not exactly along the axis, but there are other modes of a Fabry-Perot cavity. And if those modes overlap in geometry with the modes of the mirror itself, you can get a very dangerous situation. You can get the radiation pressure fluctuations that are in the light to excite the normal modes of the mirror. And we have seen that now. It's called a parametric conversion, and it has limited us, absolutely limited us in power. And these modes just keep, as you increase the power, they come up, and that's the reason why we're not at design power. Okay? Now, it turns out one way to kill it, and we tried many other ways, is to make a little gadget like this. It's a thing that people used to have on refrigerators. But what it is something you glue to the mirror, that's to the side of the mirror. This is an oscillator which has a damper. That's a piece of PZT. And that PZT is a shear mode of the PZT. You shear it, because that's one of the modes. And then you take the voltages that are developed by the PZT and damp them with a resistor. In other words, kill them with a resistor. That's what the damping is. And that puts enough damping in the system so we can now, we believe, for all the modes that have been, when we now know where they all are, we can get up to about 150 watts in the cavity now. And so we're now going to go forward with more power. It's not the heating in the mirrors that's been keeping us up. It's this thing that has held us up.
How many of these do you need per mirror to cover that?
Yeah, well, right now, we can kill all the modes with 4 of them that are important. As we increase the power more, you'll have to add more. Some which had less gain will now appear. It's an infinite number of modes in the end. But what we have proved with this, we just did this at Livingston, we proved that the big thing here was that these things don't make the noise worse in the band where we're interested. That was the thing that we were most worried about. And these are sort of very sharp damping filters. They don't do any damping in the regions from about 5 kilohertz down to 0, but they damp quite well in narrow bands above 15 kilohertz where these modes start showing up. So it's a nice gadget to have. And if we get into trouble, I'm no longer worried, as this is a limit for us. We have a way to deal with it. And
But the base itself is the same. The base is the same as the mirror, and it is attached by some.
It's glued
bonding.
by very non-smelly glue. Okay.
Oh, that's it.
Yeah, we have now a non-smelly glue. Okay. Okay, so now let me quickly go through the various fixes, and this is just, and then I'm almost done. The thing is, this is now the improvements and fixes for advanced LIGO. So now we will be operating in the next run with 70 watts, not 25 watts. We will have 3 dB of squeezing at high frequencies, so that will help with trying to find the things that Sasha, those normal modes of the nuclear fluid after the collision, for example, and also maybe in the business of looking for the damping of the tidal terms in the motion of the 2 neutron stars together, which you could get the equation of state of the nuclear material partly from the phase shifts of that motion. But you can also see them, hopefully, in these nice new oscillations that have been provided. We have to improve coatings on the ETMs. That's done. We had a fault in the coatings. It's not fundamental to the thing that I showed you. There was a bad coating job done. These dampers, which you don't know about it, this is one thing I haven't told you about. The vacuum may not have been good enough in initial LIGO at the place where you saw the recoil plate and the mirror. That space was 5 millimeters between the two. And there's water on those mirrors. There's no way to avoid it. And there may very well have been a high pressure of water. Even though you're 10 to the minus 9 in the vacuum everywhere, there might have been pressure of 10 to the minus 7 of water between the mirror and the recoil plate. And that would have been part of the reason we might have had that noise we don't understand. So most of these things have to do with trying to reduce the noise we don't understand. There was scattering. We've put a lot of baffling in. We know we have problems with charging, so we've now put on every chamber that has a test mass a way of injecting various thermal ions to making it neutral. There's an electric field meter being put inside 2 of the test mass chambers so we can find out what the fluctuation of the electric fields are. And there's some vacuum system improvements that have to be done because we have had leaks. So that's what's going on all right now. Yeah. Where was that?
Could I ask, what is the statistical characteristics of the noise you don't understand? Is it Gaussian noise or is it
No, be careful. What it is broadband noise.
Is it autoregressive noise?
It's what?
Is it autoregressive or quasi-periodic?
I can't tell you what autoregressive means. No.
No.
I can tell you exactly what it is. You take a spectrum of it, it looks like a power law.
Yeah, that's autoregressive.
That's all. Okay.
Yes. So, sir, at no cost, you can try to model that in software.
We tried, but I tell you, there's no cost. You're right. You could try. We do a lot of modeling where we understand the noise. For example, this one we haven't tried because it isn't constant.
That's okay. That's called non-stationary autoregressive noise.
Okay, fine. I agree with you. That's something I know you think you can fix.
Yeah.
And you ought to get a shot at it. Okay.
Yeah.
And I'll see if I can get people to agree with that.
Yeah.
But the thing is that the noise is most likely, my guess is it's either the vacuum, which we can completely predict, and you can't predict the individual excursions, but you can predict what it is and make the vacuum better. Well, my guess is it's either the vacuum problem, that recoil problem, or it's the charging. Now, that doesn't mean you can't do what you're saying, but I'd much rather fix it than do that stuff with do the data analysis.
Whatever you fix,
Yeah.
you could still.
You can always try to get lower.
You can always try to get lower down to Gaussian noise.
Okay.
If
Yeah, look,
say-
I agree with you. You ought to be given a chance to try that. Okay.
Thank you.
All right. So A plus. What's in A plus that's different than in now this is the stuff in the middle 20s. And what's going to be done? Frequency dependent squeezing is one of the things. We hope by that time that there is reduction in the actual coating thermal noise. We are not doing anything about that now. Can't, because we don't know quite what to do. And then this is the same thing. Lower loss optical coatings. It turns out we can probably get better coatings than we have now, aside from the mechanical losses, which is this: a larger beam splitter, balanced homodyne detectors. These are all changes that are made, and a reduction in the gravity gradient noise. That's where I'm hoping, young man, back there. This is where I'm hoping you will help us. Right there, among other places, because that's a real place. The idea here is we can do a little bit about that gravity gradient noise. Why? We can't measure, if we measure it with the test masses, you're taking out the gravitational wave. That's that bad news. And with atom interferometers and do it, that's the same problem. But what you can do maybe is measure with seismometers and infrasound pressure meters all around you. You can measure the fluctuations that are in the ground and the fluctuations that are the density fluctuations in the atmosphere, and try to auto-regress the noise that you have. It's certainly being done already. It can be done, and it's a recurrent theme. It'll be over and over again. And what you will find in these curves is people think in the A plus curve, we have tried to say we will be smart enough to have done this by a factor of 10. That's a hence we say that in the proposal. And maybe, and this is just maybe, if we get it, and this is another place where we need help, is making a conducting coating on the test masses, one that doesn't destroy the optics. Because I'm pretty sure that part of our noise will be charging. Now, Voyager is the next thing down, and I don't think I want to say much about it because I've really run out of time. Except for one thing, it's a dramatic change. It's the bottom of that curve for the noise, but that still allows you to build in the 4 kilometers. Okay, and there is and a lot of people are working on different parts of this, but there is some skepticism in whether it's actually needed. If we fix the coating problem before this, if we find that the crystalline coatings can be made big enough, or we find out how to anneal or whatever it is, put the right mixture of stuff in the coating so the thermal noise goes down by a factor of 10, we won't need this. And this is a hedge against that. And the idea is it really is a radical change in the interferometer. You go to silicon test masses, you go to a new frequency, 2 microns, you operate at 120K. This is not a trivial change in LIGO. And then the other things are larger test masses. And here's that recurrence theme that you are continuing to improve, learning how to reduce or regress out the gradients. Now finally, this is the last slide on this. This is what I think is most important right now. Since Sasha is on a committee that worries about the science of this, and along with Matt Evans and a lot of other people, Vicky Calagaro's on that committee. These are people who are preparing the science case, but there is not at this moment people preparing what I call a real engineering study of such a thing and finding out how much it might cost. I have an elementary guess, it's about $1 billion, and I wish you could make it less. The Europeans haven't even attempted a cost for their underground thing. My guess is it's about 2 to 3 billion, okay? And so the big thing here is that this is a study that's needed, and here are some topics that would be part of that study. The most important ones have to do with cost reduction, because you ultimately may want more than one of these. And even $1 billion put into a field is a big deal. So, this is not something that's going to go easy. So if you can reduce the cost, it's enormous. Most important one is making innovative vacuum systems with those long tubes. I won't go on what they are. If anybody cares about that, I'll send me an email about it. Multiple wavelength beams in other words, maybe you can not have such a good pressure by using multiple wavelengths to get rid of those phase fluctuations that are in the column of the beam tube. It turns out that's an idea that several of us have thought about. It's not trivial. And I'm not talking about multiple wavelengths. If you increase the pressure, you're going to have to change the wavelength anyway because of the Rayleigh scattering. But it's a thing that you should look at, just because it has a big factor in reducing the cost. If you could focus the beams inside the tube over 40 kilometers, that would help a lot in the costs again. But then you put something in the cavity, and that might disturb everything. So you got to think about that. Maybe there's a way to do that. Then, big cost piece is, can you find sites in the world, not just the United States, where you really get minimum cut and fill costs on the surface? Maybe where you have a bowl that takes out the curvature of the Earth, they inverts that. That would be a big step forward. It stops a lot of the costs in doing the Earth moving. So these are cost ideas to cut the costs. I'm by no means exhaustive. Nobody's really studied this enough. And then we're going to have to do some things, but they're not dramatic. You have to improve the long wavelength error, the wavelength error of the mirrors, because the scattering will be, I told you in the very earliest parts, at 40 kilometers, most of the signal will be improvement. There are a few noises that get worse as you make the interferometer longer, as an arm longer. And one of them is the scattering may be a bigger problem in a region where the mirrors have long wavelength errors, which is the hardest thing to control in a mirror. You get the scattering angles when you look at that as a grating. Instead of a grating that's got many, many wiggles, that's very broad angle. But if you have a long period on the surface, which is hard to control, the scattering gets closer and closer to the beam. And that's bad news. So you want to see if you're in trouble, we may have to make even better mirrors in terms of figure, certainly better coatings in terms of figure, and the reduction in the pendulum vertical thermal noise. And the reason for that is that wonderful pendulum when you saw with all those masses, what you're trading on is that spring noise, that the springs on the top do not, because the two pendulum are like that, they don't cause noise in the horizontal direction, the thermal noise. But as soon as you do this and you have 40 kilometers, it looks like that. And now there is a component of the vertical component along the direction of the horizontal direction. And so we probably will want to learn how to reduce, that means making springs which are more loss-free. And then, again, the same old mantra, still more reduction in the gravity gradients. Okay, so that's it. Thank you. It's up to you. I don't have to be there. The plane is at 1:42.
Yeah.
So whatever you figure out when we have to go.
We should have some time for questions.
Yeah.
Please, Satya, go ahead.
For the Einstein telescope, just because of its involved, there is a costing, but unfortunately, it depends a lot on what kind of soil you get.
I have never seen the costing. Where can I see that?
It's there in the design study document at some level. The problem of putting any number there, is really whether you get a rocky soil or a salty.
Well, of course, you're saying tunneling costs.
Yeah, because it's dominated by tunneling costs. So
is it dominated by tunneling costs?
Yeah.
Even in Europe?
Yeah.
Do you know for a fact that's true?
30-kilometer tunnels.
You mean the tunneling cost is more than the vacuum cost?
No, probably not.
Okay, that's
but,
what I'm
but
trying.
probably
Okay.
similar. So
That's very interesting. I didn't know. See, when I looked at LIGO in the beginning, the Americans, it was hopeless to do tunneling in the United States. They simply don't know how to do it. And Europe knows how to make tunnels.
I've seen numbers. I've seen numbers anywhere between 400 million to 800 million for tunneling. But if it is something that's not very rocky, it could be low. So that might be a significant cost.
Okay, let me tell you what a good vacuum study could do. Here, I'm not saying it. I mean, look, we're not going to build Einstein and a cosmic explorer. We're going to have to pick on one of them. We're going to have to pick on a controlled way to do it. I don't think it can be a free-for-all.
No,
sorry.
we need 3 detectors. Right?
You need, but you don't want to make them different, damn it.
Oh, okay.
Okay, don't do that. Don't do that. So I won't be around when it happens, but don't do it. Try to make it the same design. There's a lot of things that are cost-saving when you do that, and do it together. Don't do it
That's
separately.
the reason why there is this big study.
Yeah. Anyway, well, let me say I have numbers for the innovative vacuum system. I did the numbers. If you build even a 40 kilometers, if it's 80 kilometers of tubing, that's all I'm talking about. You build it a la LIGO, and we already went and did this very, very cheap system. It cost us $50 million in 1993. It would cost something like $800 million just for the vacuum system alone. Now, I looked at and that's terrible, because virtually a whole budget goes into that. And it turns out that if you look at what the natural gas companies do and they have tubes that are pretty big, they also have to do very good welding, but they can have things that do like that, you see. And it turns out if you do it a la their method, I'm lying a little bit here, I know you have to add something to this, but if you just build exactly what the gas companies do, it's about something around 100 million. okay? That's a factor of 8, that's a big factor. So you can have a little more, let's say you add another 100 million to actually doing something smart by having a sleeve inside and making the vacuum good. But maybe you don't need the vacuum as good if you can do the multiple wavelengths and stuff like that. So that's why it's an interesting design study. And I think the substance, I'll be honest with you, my guess is of all the topics in this thing, the one that matters the most is that one. Because it affects whether you're going for a billion or you're going for $500 million. It's a very big difference. Or maybe, hopefully, maybe 300 million. I don't know. That's something, you know, just that. There's a dramatic difference between that. I mean, that's in terms of getting money.
What are LIGO's tubes made of? Steel?
What?
Are they stainless steel?
They're stainless steel, 1/8" stainless steel, 304. We made it low hydrogen by the trickery. We made it very. The high energy community, when they heard our plans, told the NSF we would fail. And what we did is we got away with it. And it was a very critical moment in the history of LIGO. I was deeply mixed up that, and I know exactly what happened. And the thing was that we then we made the country take gambles. And it was a scary thing. You can get low hydrogen steel by cooking it. That's very interesting. You don't have to spend a lot of money. Turns out you can only even see the cost of cooking the steel in the $50 million. It's just silk. On top of that, we got rid of the water by passing 2,000 amperes through the tube. And you know, I mean, there were all sorts of tricks. And we're pumping to get 10⁻⁹ with only pumps on the ends.
Are they cryo pumps? Turbo pumps?
No, they're ion pumps.
Okay.
Ion pumps. And I mean, to me, that's a triumph. That you got. All the high energy guys said you wind up, you'll never get it. And it turns out we did. And without it, but now there's a problem. As somebody said, mice, we have problems. And the fact is, when you get a leak in a system like that, you have to find it. You can't pump it out. You have to find it. And we now have some mice that have peed on the tube. Also, we have probably microbes in the south. It turns out that's something that the Jefferson Lab ran into, and I didn't know about it. It turns out hydrochloric acid is bad stuff. That makes leaks. There are many ways you can get that in nature, but the other one is microbes, which I didn't realize. And now Jefferson Lab had problems with bellows they put on the ground in Virginia. I think we have the same problem in Louisiana because you have absolutely no problem whatsoever with the tube in Hanford. Yeah.
You said for, I think it was like, I forget which improvement thing it was, but like you